This is a Technicom podcast.
Integrated antennas. It's probably not something you often think about, but something which makes sense from a technical and aesthetic viewpoint. I'm talking about embedding antennas into the everyday objects around us. Imagine things like furniture and fixtures, which have the capability to send and receive signals from your phone. It would be a game changer, I'd say. I'm Peter Ballant from Technicon, and today we will look at how the REINDEER project can help facilitate this idea of embedded antennas by using RadioWeaves. The REINDEER consortium consists of 9 partners from 4 countries with the goal of developing the RadioWeaves smart connectivity platform as an efficient, smart, scalable, and secure connectivity infrastructure. Today we speak with project partner Erik Larsson. He's a professor and head of the Division for Communication Systems in the Department of Electrical Engineering at Linköping University in Sweden. Thanks for coming on the podcast today.
Well, thank you for having me.
The term RadioWeaves is a prominent component in REINDEER. In fact, this term was developed by the partners in the project, and we have discussed this a bit in a previous podcast, but give us the big idea here.
So radio waves, not to be confused with radio waves. Radio waves is a technical term that we have developed in the project, and that refers to a wireless infrastructure where antennas are interwoven and integrated into the environment. So, for example, they could be built into walls in a building or the ceiling or even furniture or even other objects. I mean, even pieces of art, for example. So that's where the term comes from. And RadioWeaves technology is meant to operate at low carrier frequencies. So quite generally, I mean, wireless evolves in generation. So we're now at 5G, and 5G is being deployed on a wide scale. And the academic and R&D community is looking towards the development of 6G. And in 6G, the 6th generation, there are really 2 tracks. One track is to see how one could use higher carrier frequencies. Higher carrier frequencies corresponds to smaller wavelengths. And at high carrier frequencies, the advantage is that there is a lot of spectrum available there, a lot of empty frequencies that could be used. And the other track is to develop technology for lower carrier frequencies. Lower typically means below 6 gigahertz carrier, where the wavelengths are longer. And RadioWeaves technology is developed for these lower frequencies. So the pros and cons here are really that at high carrier frequencies, so smaller wavelengths, there is more spectrum available. On the other hand, the coverage is less. The waves don't reach as far. At low carrier frequencies that RadioWeaves is being developed for, so below 6 gigahertz, wavelengths are longer, so in the order of a decimeter, and the waves tend to reach further. They penetrate better through different materials. They creep around corners and so forth. So coverage is a lot better. And it's also worth keeping in mind that these lower frequencies, which are the frequencies that have been like traditionally used in wireless, most wireless systems, terrestrial mobile radio systems at least, they remain to be the most valuable. I mean, if you look at the cost of spectrum licenses, they're almost 1,000 times more expensive per bandwidth unit per hertz. So there was this auction of frequencies a few years ago where lower frequencies sold for something like $700 per hertz of spectrum, whereas higher frequencies up below or above 30 gigahertz, they sold for $100. So there is a huge discrepancy in the value, and recognizing that, the REINDEER project and the RadioWeaves technology specifically targets how to best build infrastructure that can optimally make use of these highly valuable low frequency bands below 6 gigahertz of carrier.
And the way they do this, as you said, is embedding antennas in the objects around us. So how realistic is this if you look at towards the future?
Right, so that's the vision, right? That we, rather than building like access points or panels that you can see on, towers, for example, outdoors, right, on the rooftops of buildings, then we would rather build antenna systems that are entirely integrated into our buildings and furniture and other things that we live around and use every day. Which has multiple advantages. I mean, one, of course, is for aesthetical reasons, that we don't want ugly antenna panels all over the place. And the second is that by spreading out antennas this way, we can also cover much better the area with wireless coverage, and provide much better data rates and much better reliability of the communication links.
Mm-hmm. So another term that comes up quite a bit if you look at the website for REINDEER is energy neutral devices. What does that mean exactly?
So energy neutral devices refers to building wireless devices that don't need a power supply or a battery to operate, but rather would harvest the electrical power that they need from some source. And that source could be solar cell, could be to harvest from vibrations or from something that's moving, or it could be to harvest energy from the actual radio waves themselves. And the concepts that we're developing in REINDEER are all based on harvesting radio frequency energy, so that the infrastructure would supply this energy by beamforming is the technical term, but it really means that these antennas that are then integrated in the environment around us, they will transmit energy in such a way that these devices can receive it and make use of it. And devices in turn could be anything from like small sensors to smart glasses. You could think of like every little mousetrap out there would have would have the ability to communicate and report back if it caught anything, right? Without relying on a battery that needs to be charged or replaced, or without relying on grid connectivity in particular. So that is what energy neutral refers to.
I see. So really a great advantage when we're talking about something that's really truly wireless and not requiring any kind of external power source.
Right.
Okay. And when we spoke offline, you mentioned the idea of extreme quality of service, which is something that REINDEER could yield. What's that all about?
So quality of service quite generally refers to different things. One is data rate, how many bits per second can we transfer? The other is latency, like when I send something, how long does it take before the intended receiver has successfully decoded what I sent? And the third is really reliability or coverage. And coverage is these are intertwined, obviously, because if you don't have coverage, then latency would be like infinite, right? But coverage is really the difficult thing in wireless, and has always been. Even in the like early days of mobile telephony, the difficulty is always to cover like the cell borders when you're far from any tower. And now, speaking of reliability, then when we make cell phone calls, then we might be, or at least we've been like trained to be used to accept a coverage of maybe, let's say 95%, so that in a few percent of the cases the cell doesn't work and you need to redial or you need to move a little bit and hope you get better coverage there. With emerging applications now, with like mobile broadband and so forth, then we probably want a little higher reliability. If we play games or something over the internet, and we don't quite accept that the link goes up and then down and so on. And with applications that we foresee in REINDEER and that RadioWeaves Technology will be able to support, then we are targeting reliabilities which are extremely close to 100%. So not 95%, not 99%, but rather like 99.999 something percent. And this technology might be things that are super critical. I mean, like controlling a robot arm, for example, in a factory, right? I mean, if the link breaks, this robot might destroy some property, or it might hit someone, or cause an accident, or cause the whole thing the whole production line to stall. So extreme quality of service really refers to making wireless as robust as if we had a wired connection with a cable.
Yeah, that makes sense. And I think that's something we could all look forward to, is this higher level of service for sure. And getting back to the Reindeer project and how it's functioning so far, what kind of challenges have you seen or do you anticipate with Reindeer?
So, there are always challenges in a big project, right? But let's stay with the technical challenges, since I think those are the, the important and the interesting ones. And now, in terms of building and deploying RadioWeaves technology on a large scale eventually, I think one of the main challenges there will be to actually build the electronics and make it power efficient enough, and build the actual circuitry in such a way that it can be integrated into the environment the way that we envision. But on the prototyping stage, the research and development problems that are really hard and that we're targeting now in the project are mainly focusing on how to interconnect so many antennas. I mean, you can think of deploying hundreds or even thousands of antennas that would be spread out over a large room, could be tens of meters in size. How do we organize the signal processing? How do we interconnect these antenna units? I mean, would they be in a mesh topology, or would they be on a linear, like a stripe topology or a tree topology or something else? Should each antenna also have some capability of performing digital processing and computation? And if so, which unit should do what? How should we shuffle the data around? And so forth. So that's a major challenge. Another challenge is to synchronize these antennas. I mean, for RadioWeaves technology to work, then all the antennas need to operate phase coherently together, which means that in principle they need to agree on a global phase reference, and that requires these antennas to calibrate relative to one another periodically. So that's another major technical challenge that has to be solved, and it has to be solved in a way that doesn't cost too much resources. It's we can't afford to redo this calibration, let's say, too often. And it has to be solved in a way that's super robust. I mean, if we are targeting reliabilities up to 99.999%, then we can't afford anything to go wrong, more or less. So these are really the core technical challenges that the project is addressing in order to, let's say, achieve a prototype of the technology.
Okay, so you mentioned prototype. Is there a prototype planned for Reindeer?
There is prototyping work planned, yes. Then, of course, prototyping that can be done in a project like this will always be on a proof of concept stage. And then it's difficult to tell. I mean, how long will it take before RadioWeaves technology is adopted and deployed wide scale? This is difficult. It's a tough call to make to predict, and I think looking back at the massive MIMO story that I had the privilege to be part of, then that happened much faster than what I at the time imagined that it would. I mean, that took less than 10 years from the point where massive MIMO really was a wild academic idea, till it became a mainstream research topic in academia, till it became a mainstream topic in the 5G standardization, till it became the main underpinning core physical layer technology in 5G, which is now being commercially deployed on a wide scale worldwide. And who knows, maybe RadioWeaves will go the same path, so that we'll see it in actual action, commercially deployed in 10 years. This is really hard to tell. I mean, I'd of course hope and love that to happen, and aren't really any reasons for why it could not happen, but it's difficult to tell what factors that interplay here in the commercial world.
Well, if it does happen that it moves forward quickly, like massive MIMO, then we'll be in good shape, because this technology, I think, is a real game changer. So I want to say thank you for taking the time to talk with us today briefly about Reindeer. It's quite a pivotal project in this new world of communication that we're moving into, and you still have some time left with the project. So we wish you the best success. And again, thanks for sharing what you know today.
Indeed. Thank you so much for having me.
For more information about Reindeer, visit reindeer-project.eu. The Reindeer Project has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 101013425.